All right, we're live on YouTube for Recitation 11. So Recitation 11, we're going to actually spend more time on functions and relations because our next exam is coming up soon. And then I'm going to go over a few questions over combinatorics. So quiz number 3, grades has been posted. Remember, you have 1 week from receiving your grade to request for regrading. Quiz number 4 is going to be on November 10th, and it's going to be 1 hour window between 7:30 until 4 p.m. And tomorrow, which is November 3rd, is election day, so we will not have synchronous recitation. Hence, this recitation is being recorded right now. There would be no office hours also on Tuesday, but on Wednesday, Professor Zvang has actually agreed to give his office hour, which is from 9 to 11. So on November 4th, there's going to be 2-hour office hours. And finally, go vote. Okay, so let's record some of the properties related to functions and relations. I know it sounded a little bit while ago when we first learned this, but that's going to be on the quiz number 4. So some of those standard definitions for functions is a function is onto if for every element in the codomain is the output of some element in the domain. So one way to look into this is that if I have a function from A to B is onto if and only if for every element in the codomain there exists an element in the domain. So every element B in the codomain exists an element A in the domain such that B is equal to FA. If I want to have a mental picture, here is what I have. I have a function from domain A to codomain B is that for every element. So it's very important to say it's for every element B in the codomain, there exists some element A in the domain that map to it, right? Another way is that if I have a B prime, then something else will map to it. And if I have B double prime, some other element will map to it. Let's say this is A double prime, okay? So another way to redraw this function, if I have a picture like this, this is an onto function. Now, a function is one-to-one if nothing in the codomain is output via 2 different inputs. Of course, this is better defined when you look at if a function f from A to B is one-to-one if and only if for any xy in the domain, if fx is equal to fy implies x is equal to y. Again, this is an if and only if condition, and we're going to see very soon how to use those 2 definitions to do proofs. And a function is one-to-one correspondence, or sometimes this is called bijective, if it's both one-to-one and onto. Okay, so the first practice problem is to prove a function is one-to-one. Okay, so this is a time where you should pause the video and try to solve this on your own. Okay, when you resume, we'll go over the solution together. Okay, so here is a quick recall. How do I prove a function is one-on-one? Okay, so I'm going to use, so prove a function A to B is 1-to-1. How do I prove it? Is we suppose FA is equal to FB, and we prove that you want to show that A is equal to B. So that's how you prove a function is one-to-one. Recall in the previous slide the definition and if and only if condition. So now let's see this. This actual proof is only roughly 3 lines. So A is a positive integer, and the function fn is defined basically to be A times n, where n is an input variable. I want to prove this to be one-to-one, so here's my proof. Suppose we have two numbers in the domain such that f of n1 is equal to f of n2, then we want to show, n1 is equal to n2. If I can show ny is equal to n2, we are done by definition of one-to-one function. So this is where the one-line proof comes from. Because f of n1 is equal to f of n2, this means a of a1 is equal to a of n2, right? And you can basically cancel a from both sides because a is a positive integer, then we have n1 is equal to n2. That's it. So we start by assuming f ny is equal to f n2, and we show that n1 is equal to n2. This is how we prove a function is one-to-one. Okay. The next one is I want to prove a function is onto. Remember the definition of onto? No. A function is onto if for any value in the codomain, any element in the codomain, there exists an element in the domain that map to it. Okay. So again, if I want to show, I want to prove f is onto, how do we show it? Is we want to say, you want to show for or, let's say f is from a to b, then for or b that is in codomain, there exists a that is in the domain such that fa is equal to b. That's how you prove a function is onto. Okay. So here's my proof. To start, I need to assume there exists an element in the codomain. So in this case, I'm going to say, suppose we have y is in the codomain. Okay. And now we want to say for y in the codomain, there exists an x. We want to show there exists an x that is part of the domain such that f of x is equal to y. So this is what we want to show. But now we need to figure out what this number is. So in fact, let me make this problem slightly easier. Let me actually to say the domain is actually from 1 to infinity. Okay, so y is bigger than 1. Okay, so this way I don't have to first prove that I can take the square root. This will become meaningful very soon. So because I need to find x such that fx is equal to y. So what is a potential x? I can essentially solve x from y. Okay, so essentially we can say let my x is equal to y minus 1 square root. And because y is bigger than 1, remember I just changed the problem to make it slightly easier, then y minus 1 is bigger than 0. And then x is equal to y minus 1 square root is also bigger than 0. And let's see, right. Actually, let me even make it easier because I just realized there's a slightly interesting argument, but let's, for the time being, assuming my domain is R. Okay, so we want to say X is in R. Okay, so what does this mean? This means if X is in the form of Y minus 1 square root, what do we have? We have f of X is equal to Y minus 1 squared plus 1 is equal to y. Let's see. Oh no, actually, sorry. There's no square root again. This is equal to y minus 1 square plus 1. It's y minus 1 plus 1 is equal to y. So we just found element that is in the domain such that fx is equal to y. So therefore, y is onto. Okay, that is the end of the proof. Okay. All right. So there's another type of properties that's important when you study function relations, especially what type of relations you are dealing with. For example, a relation is reflexive even if for all element in the set, the pair AA is in a relation. It's very important is to say for all element A in capital A. Of course, irreflexive is that for all element AA is not in the relation. Symmetric is to say that if for all element AB is in A, if A and B is in R implies BA is in R. Okay. Of course, antisymmetric means that for any pair, if A is not equal to B and AB is in R implies BA is not in R. And finally, transitive is that if I have 3 elements from my set such that AB is in R and BC is in R, that implies AC is in R. Okay. And finally, a relation on A is called partial order if it's reflexive, antisymmetric, and transitive, or for short, RAT or RAT, as you could remember it. So those definitions are important to remember. So those might be good things to put on your index card for the exam. So now let's go over a few practice problems for proving or show or giving counterexamples regarding those relation properties. So the first one is that each of those 3 relations is defined on the set of positive integers. Okay, so the first one is X is greater than Y. So remember I say that, okay, so now this is a good time to pause the video again to try to solve this problem on your own. And then when you resume the video, you can watch the solutions, okay? So I'm asking those 3 relations, whether they are reflexive, symmetric, or transitive. So let's first understand what might be in those relations. So I'm going to give some examples, okay? So first of all, R is a pair of positive integers, so that X is bigger than Y. So what are some examples? For example, 2, 1 is in this relation because 2 is bigger than 1. 3, 2 is in this relation. 11, 3 is in this relation, so on and so forth. As long as the first element is bigger than the second element, that's part of this relation. Now, the second one, S, is a pair from a positive integer such that their sum is equal to 8. So what might be some examples? For example, 1, 7 is part of this. 7, 1 is part of this. Maybe 2, 6 is part of this. 6, 2 is part of this. I'm not going to enumerate all of them, but you get the idea. Okay, but keep in mind the first relation is a relation that has infinite number of pairs, but the second one is a finite because it has to be a set of positive integers. So you can actually enumerate all possible elements in the relation S. Same thing with T. Relation T, again, is going to have a finite number of, it's a finite size. So for example, what is the element in T, right? X plus 2y equal to 10. So if x is equal to 2, then y is equal to 4. That's part of the relation. When x is equal to 4, y is equal to 3, I think that's part of the relation. And so on and so forth. You can try to list the rest of the element. I'm not going to finish it. Okay. So now the question is, what are the relations between are those relationship reflexive? That's the first question. Okay. So the first question is, are those reflexive? Okay. Remember the definition of reflexive is that for all element that is positive integer, that a has to be in R. So this has to be, so a relation R is reflexive. I'm using the circle to corresponding to the words reflexive if for all a in A, where the currently A is a set of positive integer, A and A has to be in R. Okay. So the turns out is none of them is reflexive. Okay. Why? Because you can give example. Remember, 1 is a positive integer. For all those relations to be reflexive, 1 and 1 has to be part of the relation. But it turns out 1 is not part of R. It's also not part of S. And also is not part of T. Okay. So neither of those relations contain the pair 1, 1. But you might argue to say, well, look, so relation S contains the pair 4, 4. But that is only one sort of, symmetric reflexive pair, but it's not applying to all positive integers. Okay. Now let's ask the question: are those three relations symmetric? Remember the definition of symmetric. Let me use S. If, right? So if you look at the definition, it's symmetric if for any AB implies BA is in R. So for all AB is in R, AB in R implies BA is in R. Okay. So if you look at this definition, R is not symmetric. Why? Because 2 and 1 is in R, but 1 and 2 is not in R, right? Because 2 is bigger than 1, but 1 is not bigger than 2. So S is symmetric. But actually, let's try to prove it. And finally, T is not symmetric. Why? Because 2 and 4 is in R, but 4 and 2 is not in R. And you can validate this very quickly. So what's left to be done is to prove S is symmetric. So how do we prove that? Okay. So I'm going to try to add a page. Okay, so now we want to show that the relation S is symmetric. So remember, we want to show that, when something is symmetric is whenever AB is in the relation, BA is in relation, okay? So first of all, the version number 1 is you can list all elements in the relation S. Because remember, S is defined by X plus Y equal to 8, right? And also X has to be, both of them has to be positive integer. So if I enumerate all the elements, you can see that it's symmetric. But if I want to prove it more generally, okay, is I want to show it's symmetric, then we can say, well, that A and B is part of the positive integer, suppose the pair AB is in S. So what does that mean? That means, let's use XY instead. Sorry. If I have two element X and Y, right, is a positive integer. Suppose the pair XY is in this relation, that means X plus Y is equal to 8. I can permute it and not changing the equality, which is Y plus X is equal to 8. This implies by the definition of S, Y of X is part of S. Okay, so that is a proof that, the second relation S is actually symmetric. Now, finally, the question is that, is this relation transitive? Okay. So what I would like you to do is to do this as a take-home exercise and convince yourself whether it's transitive or not. And if you get stuck, please feel free to pose this question on Piazza. But by definition, you should be able to show whether those relations are transitive or not, right? I'm saying it's transitive if I have three elements in the set. If A and B is in the relation and B and C is in relation, implies A and C in the relation. Okay. So now remember we have learned proofs from chapter 2, but for the rest of the semester, you are always going to get some sort of proof related to the topic of that chapter. For example, here, I want you to prove that if R is any relation on a set A, show that R intersect R inverse is symmetric. Okay, so this is a proof regarding relations. Okay, again, this is a time where you can pause it and try to see if you can prove this. A quick hint of this, this proof is roughly 6 lines, and it's going to use the property of set relation, and it's going to use the property of intersection. Oh, actually, to make it easier, I think I made a typo here. Actually, intersection is fine too, but I actually made a typo in my question. Let me change this. I want to prove the union is actually symmetric. Okay. All right. How do you prove something is symmetric? Let's go back to the definition of symmetric relations. So something is symmetric even only for two elements if AB is in R, implies BA is in R. That's what we want to show, okay? But here it's an intersection. So what we do is we want to show, our goal is to show this relation is symmetric. So again, this is where you can pause the video and try to solve it on your own, okay? So suppose A and B is part of the union of these two set of relations. We want to show that BA, right? We want to show B of A is also this relation. So that is the symmetric situation. So let's say, okay, so because AB is in, because the pair AB is in R union R inverse, that means AB is either in the first set or is in the second set. Okay, so that means now we have two cases. So case number one, if AB is in R, okay, that's the first case. So by definition of inverse, if AB is in R, that means BA is in R inverse. Of course, here we do assume the relation R is invertible, right? And it is. So BA is in R inverse. So what does this mean? That means BA is going to be in R union R inverse, right? Because it's already in a set R inverse. Of course, when R inverse is union with another set, it's still part of element. Now the second case, so this is case 1, this is case 2. If AB is in R inverse, again, by the definition of R inverse, that means AB is in R. Okay. And this means, oh, sorry, a BA is in R. Okay. And this implies BA is in R union R inverse. Okay. So now I start with assuming AB is in there, and I showed for both cases, BA is also in there. That means it's symmetric. So that is the end of the proof. So therefore, R union R inverse is symmetric. So that's the end of the proof. Okay. All right. Next one. If R and S a transitive relation on A, show by a counterexample that the following need not be transitive, and the following is R union S. Okay. So this is a good time for you to pause the video again and see if you can come up with a counterexample. And when you resume the video, you can try to look at the solution together. Okay. So it turns out there's an interesting play of the definition of what is meant by transitive. Okay, so here's a counterexample. My R can be a relation that only contains a pair. Okay, so A, let's say A is a set A, B, and C. And R is a relation on A that only have one pair. S is a relation on A that, again, only have one pair. And it's actually interesting in both cases, even though R and S only have one element, is actually transitive. So both R and S are transitive. But now if I take R union S, we have AB, BC. So now you can see that this is not transitive. So we start with both R and S are transitive, but R union S is not transitive. So here goes your counterexample, okay? All right, so now we're going to go through a few more examples on functional relations. They're fairly straightforward, okay? So the first question is, I give you a set A, and I give you a relation. Is it reflexive? So again, reflexive, it has to be for all A in capital A, AA has to be in the relation, okay? So the answer is, well, please pause the video and then resume it. So the answer is no, R is not reflexive, right? Because, for example, 1 and 1 is not part of R, okay? So then the next question is, how do we make it reflexive, okay? As I hinted before, you need A and A in there. So basically what you need to do is essentially you want to add the pair 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4 in there to make it reflexive, okay? So that's exactly what you do. So you define a set F by all those pairs and you union it. That's how you make the new set of relations reflexive. Now the interesting thing is that if I give you this, is this symmetric? Okay, so remember the idea of symmetric is to say that, well, you know, if A and B is there, then B and A has to be there. Okay. So it turns out the answer is no. You need to add a little bit more things to make it symmetric. So this is where you can pause the video and see what do you add to it. And the answer is you need to add some pairs to make it symmetric. For example, 0, 1 is in R, but 1, 0 is not in R. 1, 2 is in R, but 2, 1 is not. And 0, 2 is in R, and 2, 0 is not. So you need to kind of add those missing pieces to make it symmetric. So now if you union R and F and S, it's both reflexive and symmetric now. Then the next follow-up question is this thing transitive? Okay. So remember, what is the definition of a transitive? If I have A, B, and C, that's part of A. If A and B is in R and B and C is in R, this implies A and C is in R. Okay. So that's the definition of a transitive. So you kind of want to check all those relations. But there's another way to try to, so the answer is, of course, yes, this is transitive, but how do we check it in a reasonable way? One way is you take any two pair, like A, B, and B, C, and check if AC is in there, okay? Another way to think about this is actually using a directed graph or the arrow diagram to actually visualize this relation. Okay, so what is this? So I have 0, 1, 2, 3, and 4. So those are element. Okay, actually, let me simplify it. So I just draw the element itself. So it's 0, 1, 2, 3, 4. So the first pair is 0, 0. So it's a self loop. Then 0, 1, and then 0, 2. Right? I'm just going from left to right over here. And then 1, 0, double arrow, 1, 1, self loop, 1, 2, 2, 0, double arrow, and 2, 1, double arrow, and then 2, 2, self arrow. And then I have 3, 3, self arrow, 3 to 4, 4 to 3, and 4, 4. Okay. So that is a graph of this relation. And now you can say, okay, how do I translate to a transitive relation? That means each time I go through two arrows and to see whether there is a conflict. For example, if I go from say 0 to 1 and then 1 to 2, is there arrow from 0 to 2? Yes. Okay. If I say 3 to 3, 3 to 4, is there arrow between 3 to 4? The answer is yes. So you can actually check those by going over this this diagram. Okay, and the answer is yes, this relation is transitive. Now, finally, so now the relation is reflexive, symmetric, and transitive. Therefore, it is an equivalence relation. Okay, and once you have equivalence relation, it induces, right? It's equivalent relation if there exists a partition. So now the question is, what is a partition of my set A? And the answer is actually going back to this picture here. This is exactly the partition. So the partition, they basically correspond to island in my diagram. So in this case, my partition is that A is equal to 0, 1, 2, union 3, 4. That is a partition. Okay. All right. Okay. So now we have reviewed a bunch of questions for function and relation. Let's go over a few questions we have learned so far with combinatorics. Again, combinatorics is going to be in quiz number 5, not quiz number 4, but let's start reviewing some problem for that as well. So there's two notations, right? So one is P of NR. This is counting the number of permutations of n objects taken R at a time. So when we say permutation, that does mean the order matters. Okay, so the formula of nr is n factorial over n minus r factorial. Okay, and this is of course equal to n times n minus 1, n minus 2, up until n minus r plus 1. Now the second definition that's going to be useful also is counting the number of combinations. So this is counting the number of combinations of n objects taken R at a time. So what's the difference? In this case, when taking the combinations, the order does not matter. Okay, so essentially, this is alternatively is number of R element subsets of a set with n elements. Okay, so the key is subset. When you take a subset from a set, the order of element in the subset does not matter. Does not matter, okay? The formula goes, if I choose R element from n, then it's n factorial of R factorial n minus R factorial. And this is really the important part. This is try to factor out all the permutation of the R element because among themselves, the order does not matter, okay? And this is of course equal to P of nr over R factorial. Okay, so this is a quick report of definitions. Let's look at a few simple examples, okay? The first example is find the number of ways a judge can reward first, second, and third place to a game with 18 participants. Again, please pause the video and try to solve this on your own, okay? So how do we solve this? One way to think about this is that there is 3 spots I need to fill. Correspondingly, there's the first place, second place, and third place. When we try to fill the first place, I have 18 choices. And when someone taking the first place, the remaining 17 people can potentially take the second place. So you have 17 choice for the second place. And similarly, after the first and second position has been taken, then the last position, you have 16 choices. So the final answer is 18 times 17 times 16, which happened to be 4,896. But this is also, by our formula, this is taking 3 out of 18 in terms of permutations because the order does matter, right? So that is why we're using the permutation formula, okay? So this is fairly straightforward. Let's look at a slightly more complicated problem. Let's say you have a team of R number of Americans and S number of Germans. Of course, in this case, to make it easier, no one has dual citizenship, okay? So now the question is, find the number of ways they can sit in a row if all Germans have to sit together, okay? So again, please pause the video and solve it on your own. This should take you less than 2 minutes, okay? So when you come back, now let's solve this together. What is the condition if Germans have to sit together, right? And then all those are represented by variables. So what does that mean? When Germans sit together, that means I can kind of glue them into one single unit that they have to be together in a row. So I'm just going to put all the German participants here in this box to represent that they are all together in this permutation problem. Okay, so you have all of them in one sort of unit, okay? So now, well, we don't have any regulation of how Americans are going to sit. So maybe there is 0 American to the left of it, or 1 or 2, and then remaining is going to be on the right. So to the left of the German students, we can have 0 Americans. And then on the right-hand side, maybe there is R American. Okay. And now you can have 1 American to the left. And then you have R minus 1 to the right. And so on. And finally, you can have R American on the left and 0 American on the right. So those are all possible ways to sort of looking at the relative position between American and German students. So total, there is R plus 1 ways to kind of split, the Americans into 2 parts, to the left of the German students and to the right of the German students. But however, remember, in this case, we're looking at a number of ways and the order does matter. So we are also inherently talking about a permutation problem. So you have R plus 1 different ways to split the American student and then into 2 parts. Among the German student, there is S factorial number of ways to permute all the German students among themselves. And there is R factorial different ways to permute the American students. So that is the final answer. Okay. Now let's make it slightly, well, I wouldn't say harder, but a slightly variation of this question. Is again, I have R number of American students and S number of German students, but I want to make sure that all the American students are sit together and all the German students are sit together, okay? So now this is a question of, I put a little bit more constraint to it. So you should be able to solve this again within roughly 2 minutes, and you can pause the video now. Okay, so now let's look at how to solve this. Because all the American students have to sit together, so I'm going to put them into one single unit. Those are all the American students. And this unit is all the German student. So there's actually 2 ways, right? Americans all sit to the left of the Germans. All the Germans sit to the left of Americans. So there's 2 ways of doing that. But similarly as before, for among the American student, there's a permutation. So that's that is R factorial. Among the German student, there's a permutation. So that is S factorial. So that's the final answer. Okay, so I'm going to fast forward a bit because this is not going to be this is just a recitation. So I want to review one more problems surrounding combinatorics. And in this case, we're talking about not counting, but probability now, okay? So we have seen a few problems regarding like sort of World Series and so on and so forth, or best of 5, best of 7, and so on. So this is an example again about best of 4, right? So 2 teams are going to play the World Series until one of the team has won 4 games. And assuming that each game played is won by team A with probability P. Oh, and of course, let's assume, yeah. So let's assume also each game played by team B is won with probability, let's say Q, okay? So now I want you to kind of write out what is the probability that team A wins in n games where n is equal to 4, 5, 6, and 7, okay? So again, you can pause the video and try to solve this on your own. The first case is that if A wins in, say, 4 games, right? So let's say A wins in 4 games because n is equal to 4, okay? Then what is the probability? Because we say that it's won with probability P, but also, okay, additionally, we also assume, A wins a game in a sort of independent way, okay? So if it wins 4 games, each time it has a probability of P of winning, then the probability of A winning 4 games is P to the power 4. Now, let's say N is bigger than 4 now. So that means A have to win 4 games, but they are not necessarily consecutive. Not necessarily consecutive, okay? So it needs to win 3 games for the first N-1 game, and it has to win the last game. So in order for A to win, it has to win, among the first N-1 game, it has to win 3 of them, and then it has to win the last one, okay? So I have, among N-1, I'm going to choose 3. So, okay. And then the probability of A winning is P to the power 4. The probability of B winning is N-4. So that's that. Okay, so now finally is the probability of A wins after 4, 5, 6, 7 games is adding those 2 terms together. Okay, so that's that. But this is just a simple exercise where I want to test, this particular formula here. And the trick part of this problem is to understand if A have to win in a game more than 4 games, A has to win the first 3 games among the first N-1 game and the last game. That's how N wins the whole series. Okay, so really the key part is what I highlighted in yellow. That is a hard part of this question. And we did not give the actual probability because we just want to see a formula here. Okay. All right. That is for now. Oh, actually, sorry, let me make a correction. Sometimes we actually write this, you don't put C in front of it. In some sense, if you see N of R is written like this. So let's be consistent. Okay, so this is what I want to write. Okay. All right, so good luck with your upcoming quiz, and I'll see you next week.